In this video, we're going to see the rule number 2 of root locus in control systems design. The rule number 2 statement is, as k is increased from 0 to infinity, each branch of the root locus originates from an open loop pole as k equals to 0 and terminates either on open loop 0 or on infinity as k tends to infinity. We are going to see the proof for it in this video. To prove this, let's take open loop gain, which is g of s times h of s, as, let's say, we can write this as k times the numerator polynomial n of s divided by the denominator polynomial d of s. Suppose this is how it is. Now the parameter to vary in order to see the roots of the characteristic equation, let's say it is k here. Okay, so now we are going to see the roots of characteristic equation. If you're given open loop gain like this, g of s times h of s, the characteristic equation is 1 plus g of s times h of s. This character equals to 0. This is the characteristic equation, right? So this characteristic equation is nothing but that this function, which is 1 plus g of s h of s, is the denominator of the closed loop transfer function, right? So here, let me take this g of s h of s thing here, k times n of s divided by d of s. Now from this, let's take, if n of s equals to 0, then the roots of this n of s are nothing but zeros of, let me write down here, zeros of g of s times h of s. Okay, now if we equate this denominator to 0, say d of s equals to 0, the roots of this equation are nothing but poles of open loop gain, which is g of s times h of s, right? These are two important statements here. Now we are writing this characteristic equation in this form. Now we are going to change k from 0 to infinity and see how the roots of this characteristic equation are going to change. Okay, now when k equals to 0, we can rewrite this function, this characteristic equation, as d of s plus k times n of s equals to 0, right? So now if I substitute k equals to 0, then the roots of characteristic equation are the roots of this d of s equals to 0. This d of s equals to 0 roots are nothing but poles of g of s h of s. So it means when k equals to 0, roots of characteristic equation are nothing but the poles of open loop gain, which is g of s times h of s. So for k equals to 0, we have seen. Now when k is tending to infinity, let's take the same equation. Let me rewrite this here. Okay, say d of s plus k times n of s equals to 0. Now if I'm making k tending to infinity, then it becomes the way we write it becomes really confusing because it is tending to infinity and this is 0. So we have to rewrite this taking k common here. So we'll have 1 over k times d of s, okay, plus n of s equals to 0. Now we are taking k equals to infinity here. In that case, this term becomes 0. Now the resultant equation will become n of s equals to 0. Now the roots of this n of s equals to 0 are nothing but the zeros of g of s times h of s. It means as k tends to infinity or k equals to infinity, roots of characteristic equation are nothing but zeros of g of s h of s. It means as you are varying k from 0 to infinity, the root locus for this characteristic equation is going to go from poles of g of s h of s to zeros of g of s h of s. If we take an example, let us take g of s h of s to be like s plus 2 divided by s plus 1. Okay, let me take this example. Suppose this is let's take k also. Okay, g of s times h of s. Okay, now if we plot this here, okay, let me take -1 is the pole, right? And take 0 here, which is -2. Now when k equals to 0, the roots of the characteristic equation are nothing but the root of the characteristic equation will be this pole. Okay, and when k tends to infinity, the root will be this 0. Okay, when k tends to infinity, this is when k equals to 0. It means as k is increasing, this plot, let me take a different color. Okay, this pole is going to move in this direction. Okay, and as k tends to infinity, it is going to go to this point. Okay, this is how the root locus looks for this one based on this rule number 2. Okay, the root locus starts from the open loop poles and it ends at open loop zeros for this characteristic equation roots. Okay, and in general, the numerator polynomial order, if you take m, and the denominator polynomial order, let's take n, usually we'll have conditions where m is less than n. Okay, this is usually called as proper fraction. Okay, now if m is less than n, usually what happens is n minus m branches of this root locus are going to tend to infinity, and this n minus m, okay, m branches are actually going to terminate at these open loop zeros, and the remaining, which is n minus m, will tend to infinity, and we'll see about this in the next coming rules.